So, okay, let us start. We are somewhere in the middle of discussing the continuity properties of the Brownian motion. And so let me start with some reminder and some more comments. Continuity properties of Brownian motion. Now I'm just going to list several facts on this. So the fact number one is that almost surely it is not differentiable anywhere. So almost surely for any t this lim sup over h to alpha is plus infinity. And yeah, for any alpha greater than 1/2. Okay? So the second fact is that, okay, later I'm going to comment how it's proven, but okay, let me just list several facts. Second fact is Levy's theorem on the modulus of continuity, which says that, again, almost surely, okay, sorry, here it was this way. So almost surely, these lim sup, say 1 minus h, over 2h log 1 over h is 1. The third fact, and we are in progress of proving this result. We already did one of the bounds and we are going to do another. So the third result I also mentioned last time is Hinchin's law of iterated logarithm, which says that, again, almost surely, if I just think about a given point, say the origin or any other point, then bh over log 1h is 1. And to complement this list, it was a question last time if there are points where the Brownian motion is 1/2 Hölder continuous, and the answer is yes. So I didn't know the answer last time. It was a shame. The answer is yes. So in fact, if you take, again, almost surely, if you take the infimum over all t, say 0, 1, of this limit with just square root of h in the denominator, then this is again 1. So just to give a sort of a perspective, and there is no contradiction anywhere. So to give you a sort of a perspective, basically at a typical point, in particular at any fixed point, the local behavior is given by Hinchin's law. So the local growth rate is square root h log with this explicit constant. Nevertheless, there are exceptional moments. So in particular, almost surely there is a moment, so you don't know where it is exactly, but nevertheless there is some t such that this limit, the local behavior is square root of h. And it cannot be smaller, so again the constants are pretty sharp here. And at the same time, from Levy's theorem, we know that there are some other increments that are in fact larger. Okay? To give an intuition why it's not contradictory, just think about a very caricature example here. Say what happens with Poisson process. So it was a series of jumps, right? Defined this way. And then what you know is that for any given t, almost surely this process is continuous at the point t. Okay, let me t naught. At t naught, right? Because the probability that you find a jump exactly at t naught is 0. There are only countably many of jumps. And at the same time, you know that almost surely this is not continuous. At least on 0 infinity. Because there is at least one jump. And there is no contradiction. So this interplay of two statements almost surely and for any t is actually rather deep because of non-countability of the set. Okay? So now let me remind what happened here. So this I'm not going to discuss at all. If you need more information, just see yet another book by Peter Morters and Yuval Paris, Brownian motion. So actually there are many beautiful results of these sorts. In particular, you can try to optimize not over a single point or the whole segment like here, but over some counter sets, and ask what is the typical behavior on a given counter set, something like that. Okay, just take a look on this book. So this is going to be an exercise. I'm not going to discuss this on the blackboard. Not now, probably, most probably in 2 weeks. So it will be the week when I'm not here. And so what I suggest is to discuss this all together, following some plan with Marianna. So this we already have proven. So here, this is still a reminder, what was the idea? The idea was actually quite simple, to consider events like, let me denote them like this, which is the event that the increment of the Brownian motion from here to there, on the dyadic rational segment, that this increment is less than, okay, some constant depending on, let me put it here, and say over j, by what it should be, 2 minus n to alpha. To consider these events, and then to say, okay, let this be just the intersection of this and kj. So this is the event that the Brownian motion has a small increment, I mean relatively small increment on this interval. And this is the event that it has several small increments in a row, right? And m was chosen so that this is less than -1. And then basically, if you just later define the event that this happened at least once, like this, maybe -1, that this happened at least ones on the segment, then basically what Borel-Cantelli tells us is that it happens only finite number of times. So in particular, it cannot happen with for all the n's increasing to infinity. And at the same time, we know that if a good t, I mean, satisfying this condition exists, then, okay, this happens for all n tends to infinity near t. And if there is a good point somewhere here, then from this condition it follows that the Brownian motion has many relatively small increments. And this is just impossible due to rather simple computation. Okay, here again we already did one of the bounds. So what was done? We checked that actually, okay, part easy bound. So the easy bound was that this lim sup is at least 1, right? This was an easy bound. And, right, if it what we did? Yes. And the equivalent way to say it is that almost surely this lim sup is less than 1 minus epsilon. Okay, that the probability of this event is 0. Okay, that this cannot happen. I mean, if we know that the probability of this event is 0, then almost surely this is greater than 1 minus epsilon, and since it holds for any epsilon, then it's greater than 1. Okay, so to prove this, again, what we did is actually very simple. So just take h 2 to minus n, consider all t of the form dyadic rational with this denominator, and then just estimate, just compute the probability, that this increment is less, okay, what less than what is supposed to be. This is just a straightforward computation, right? This is something about normal variables. And then you just see that, okay, here there is some answer, and then there are 2 to n independent increments. So you can compute the probability that actually all these increments less than 1 minus epsilon, blah, blah, blah. And you just see that it decreases exponentially. And because of that, only a finite number can happen, and we are done. So it cannot happen for all n's eventually. So now, okay, this was a reminder. And now let me start doing the other bound. So we continue the proof of Levy's theorem. So now what we want is to show that actually it cannot be smaller. So wanted that this lim sup of increments is okay, less than 1 plus epsilon, almost surely. Probability. This is 1. Okay? So that's what we want. We would like to control all the increments simultaneously. And somehow I insist on this explicit saying all the increments because of this diversity of results. Right? This is important. So what we need is to control all of them. What is the idea? The idea is, again, consider dyadic intervals. Right? But now we should be more careful because we cannot just take several of them, I mean a finite number of them, and estimate something. Because we need to consider all the t's at once, right? So we need to consider all the refining dyadics. So what we are going to do, let me check. So let me define this event. Okay, where is the event? Yeah. So n is again the level of dyadics. So k and L are just some indices in between 2 to n. And this event is actually what I would like to do is to consider a bad event when b 2 minus nl minus b2 minus nk is actually greater than 1 plus epsilon, what it should be. And h here is of course nothing but the increment. Okay, so this is the bad event. That's what I would like to forbid. Then let me consider this. I mean, this is going to be the event that something bad happened at the level n. Okay? So basically this is just the union of all nkl, where again k and l are two indices. But actually I do not need to consider all the increments simultaneously. So somehow I should focus on small ones, right? And now I just consider all of them. So what I also would like to include here is that this difference is relatively small. In principle, you can just say that L is k plus 1. The only problematic fact with that, I mean, so everything goes smoothly, but then you do not see the explicit constant 2 here. What you have is some constant. So because of that, let us slightly enlarge. So delta is going to be fixed later on. This is some parameter. So what I consider is all dyadics at level n, which are quite close to each other, right? But nevertheless not consecutive. Delta is fixed later. And then I'm going to estimate the probability of this event. I'm going to prove that it does not happen eventually. So what is the probability of these? This is again just the story about normal random variables, right? So what's that? This is just the probability that the standard normal variable is 0, 1 is greater than 1 plus epsilon square root log 1 over h. This is h. This is the 2 log 1 over h. So here is exactly the variance. H is exactly the variance of this variable. Okay, so, and we are going to estimate everything from above. So what I'm saying is that this is less than 1 plus epsilon by this square root. What is the square root? So this is the constant maybe I'm just not going to write everything here, let it be just constant. So this is the constant. H is of order what? Is of order 2 to delta n at most. Okay. So what I'm going to say is that here this is constant over square root of n. Is clear what happened? No, maybe I'm cheating, so this is not the case. Anyway, so this is not the most important. This is not the most important term. So let me write everything explicitly. And here again, so what I'm using is the bound that the probability that the normal variable is big is relatively small. So what is the bound? So this is e to minus 1 plus epsilon squared logarithm 1 over h. And maybe there is another 2 here because of the 2 tails, but again, this is not of importance. It's clear what happened until now. So I just used the standard bound that the normal variable is greater than a with probability 1 over a exponential minus a squared over 2. Yeah, so here it's just again the standard bound of the large deviation of the random variable. So, okay, let us now think what's here. So what is h? H is 2 to minus n, maybe multiplied by something 2 to delta n, but anyway, the logarithm is of order n, right? So everything here is just 1 over square root of n, but this is not of big interest. So what is of some interest is how fast it decays here. So what I would like to say is that this is 2 by all this. Again, so h is roughly 2 to the n, right? So what I would have here if it was 2 to the n is just 2 minus 1 plus epsilon squared n. But actually it might be slightly bigger, right? Because of this L minus k. So because of that, I have here another 1 minus delta. Is clear what's going on? Or not that much? I mean, so if you have some questions, just please ask immediately. Because there is some computation, it is not very hard, but you know, it's good to follow what goes on. So again, just if we think about 2 consecutive L and K, then there is no delta here, and this is somehow more transparent. Okay, good. So here is the estimate, and now, okay, this is for a single event, and now what I'm saying is that the probability of the whole delta n, I'm just using the union bound. So it's bounded by square root of n to the number of these guys. So what is the number? The number is n plus delta, n1 plus delta, because there are 2 to n options for k, and then here 2 to delta n options for the increment, by the same. In particular, given epsilon, I can tune my delta so that this kills that. Okay? Now tune delta so that the second factor wins. Okay? If we tune it in this way, then again, only finite number of the events can happen.
it always possible to choose delta?
Yeah, sure, because if you just take 0, then it's true, and then by continuity you see that there is some gap, right? I mean, so you can solve it explicitly, of course, but what I'm saying is that if it was allowed to take delta 0, then it's possible, but definitely this is a continuous condition, so there is always some gap. So we start by fixing epsilon here, and then we adjust delta there. Okay?
And so at this point, nothing wrong with picking actually delta equal to 0.
At this point, there is nothing wrong, but what I need in a minute is strictly positive delta. Okay, so I need something. Okay. So what we gained? Let me rewrite it. So we gained that there exists some level which is random, which depends on the event, such that for any, for any sharper partition, for any two indices such that, less than delta 2 to delta n, we have the opposite, right? We have b2 to minus nl, 2 to minus nk is less than 1 plus epsilon square root 2h log 1h, and h, it's always just the difference. So this is a temporary variable. Okay, so here now is our segment, and we know that given a sample of the Brownian motion, for almost all the samples, for the set of full measure. So given a sample of the Brownian motion, there is a level such that the behavior, I'm splitting in 3, okay, these are not dyadic rationals, but nevertheless, the behavior on all the small segments is good. And now I'm going to pass from dyadic intervals to all the t's. So now we have some information on rationals, and now we need to push it forward to all the t's. So now consider some pair t and t plus h. It would be t plus h with h less than 2 to minus n. So now h is going to be the continuous variable. So I just take 2 points here and say there. And let this h is roughly, sorry, it should be some adjustment here. It should be, I think, 1 minus delta. And let h is roughly, roughly this with some n, which is greater than n capital. And by roughly, I mean like this. And write there's two arbitrary real numbers, non-rational numbers, in the following way. So t is gonna be 2 to minus n k, k 2 to minus n, plus, say, whatever, alpha n plus 1 to minus n plus 1, plus alpha n plus 2 to minus n plus 2, plus etc., where those are just binary digits. I mean, so I have some arbitrary point on this segment. I know something about dyadic rationals, and I just try to think about.
You mean minus and minus 1?
Yeah, first it should be minus, and second, I think here I need minuses also. Yeah, okay. Well, I would like to think about this increment from t to t plus h in the following manner, so that there is some big increment at the level n, and then there is a sequence of smaller increments, possibly infinite, here to the left and here to the right. Here there is a sequence of smaller increments. Okay, so then what I would like to write is actually this, I mean, with pluses.
But the two numbers have a distance at least 2 to the minus n. That doesn't mean that they have the adic expansion starting from that level.
They have what? Say again, please.
If the two numbers have a distance at most 2 to the minus n something, that doesn't mean that they have a dyadic expansion starting in that
K
level.
is not necessarily 0, 1.
K and L are not 0, 1. K and L are exactly the same as there. I mean, they're just.
Are not necessarily.
K and L are not, but these are just digits. I mean, so I keep track of first n bits here, and these guys, I mean, all betas and all alphas are in 0, 1. And then, so what are K and L? So actually, what we do know is that, so we know, is it here? Just by construction, that L minus K basically is roughly 2 to n delta. So the distance is roughly 2 to minus n, 1 minus delta. So here it's roughly 2 to n delta. And in fact, it's less because I've just chosen pluses here and minuses here. Okay? It's clear what happened. I mean, so again, if we are not interested in the sharp constant 2 here, then we can just remove deltas everywhere. Think about delta to be 0. And then just take n to be the first bit when those two expansions are actually different. But here, this is slightly more involved, but really, you know, by tiny amount. So the first increment is relatively big. I mean, this is still exponentially bigger than all the others. Okay? So here is the construction, and actually now that's almost it. Where should I continue? Okay, let me maybe continue right below, if it's still visible. I don't know if it's still visible, say until here, guys. Nope. Okay, then I try to continue above. So now what I'm saying is that we have this increment, and what we use here is that this is a continuous function in t, right? So we can approach any moment by dyadic rationals. So we have a bound which is of the form, okay, there is the main term which comes from here. And then there are some remainders. And all the remainders, well, even if all of them are there, I cannot have more than 2 minus m log 2 to m. Even if all the digits are non-zero here, I cannot have more than this sum, because I have control on all the on all the increments there. And this, and it should be 1 plus epsilon somewhere, right? Because in my event I had 1 plus epsilon. So, okay, 1 plus epsilon. And this is bounded by 1 plus epsilon square root of 2h log 1h. And remember that again, this is roughly 2 to minus m, 1 minus delta. So now what I'm saying is that if I just had delta 0, then basically this and that are of the same order. So what I would have are just 3 terms of the same order. But because of this small trick, now this is smaller than that, right? Because it starts with 2 to minus m. So I can conclude from here is that altogether this is less than, say like there, provided m is large enough. So what happened? I just said that the whole sum is less than epsilon by the first term. By this term, by the leading term. And now, yeah, I claim that we are done. Okay, so what I did, I proved that for any pair, for any increment, starting, I mean, what I proved, that for any sample of the Brownian motion, there is this n capital. Then, having this n capital, I can take h small enough so that it's smaller than here. Here it's written. So for any given sample, there is a level so that all the increments over dyadics are under control. And then if all the increments are under control, and since I already knew that BT is continuous, I can control all the increments simultaneously, not only even over dyadics. So we are done, and basically the question, is the overall strategy clear? I mean, what happened? Okay? Well, good. Again, so if it is too hard and too technical, just think first about the case when there is no delta at all. When you have just the control of successive of increments, right? And then think about just general t plus h and t and split it into dyadics and sum over all the increments. So basically what you gain is, is another constant here, like 3. Okay, perfect. Now, yeah. Actually, I need this scheme for the second half of today's lecture. So because of that, let me erase everything here. And what I'm now going to do is to discuss yet another approach to the Brownian motion, which does not follow any explicit construction like we did, for instance, in the Fourier basis or in the Harrer basis, but instead, somehow it's even more natural. Instead, it uses the following philosophy. So remember that what we need is a Gaussian process. So this is a collection of variables indexed by by the unit segment, for instance, with a given covariance. And we have a very workable understanding of what the Gaussian vectors are. If the set of indices was finite, then there is no problem. It's just a Gaussian vector in the finite dimensional space. And again, so if the set of indices is countable, then we do not expect that something interesting appears, right? Because countable sets, okay, they're nice. You just use some, some construction, and you can speak about all this more or less explicitly. And then it's tempting just to say that, okay, let me first define the Brownian motion on all the dyadic rationals and then somehow continue it. And maybe what I have at the end of the day is exactly what I need. So this is the way I would like to discuss. And the basic reason why I pay so much attention to the construction of the Brownian motion is basically because later during this year, for instance, in Zurich, you will have a course on the Gaussian free field, which is a very similar object, but in 2D. And somehow, for this object, it seems to be quite important to understand what are the ways to think about it. It's more complicated than the Brownian motion because the set of indices is not any more ordered, and there are tricky issues with geometry. And so, because what you are going to see is a more complicated object, but more or less of the same style, I'm really trying to focus on several ways to think about something very well known. Okay, so next paragraph is Kolmogorov's continuity criterion. Construction of the Brownian motion through finite dimensional marginals. And let me also include Donskir's theorem here. This is the very classical result, which says that any random walk, trajectory of any random walk, then probably rescaled, converges to the Brownian motion. So let me include this into this paragraph. Okay, so and to start with, even before the break, it's going to be something about measure theory. So measure theory reminders. So right now we are going to think about collections of random variables labeled by some set. Okay? So we are changing the perspective. We are not thinking about this as a random process, but just a collection of variables, which is a weaker notion. So what is their first important reminder? It's called Kolmogorov extension. Theorem or lemma. So what does it say? There is something here, nothing very deep, but something that maybe is good to digest during the break. So what does it say? Imagine that we have, for any finite set of indices, say on 0t, we have a measure defined on no, not be frightening. It's going to be some notation. Okay, what is here? I mean, if I is a finite set, then this is just a finite dimensional set, finite dimensional space, just Rn. And this is just the tensor product of Borel sigma algebras, which is again the Borel sigma algebra of this one. Okay? So this is and this is just a measure, probabilistic measure, okay, where this is a probabilistic measure which should be thought as a distribution of some random variable in this space. And what you ask is that there is a consistency condition. So consistency conditions say that if you consider a larger set of indices, so if you think about more times, then one of the measures is just the projection of the another. There is a formal way to write it down. Maybe it's better to write J here. So what's that? Just imagine you have, I don't know, R3, which is J 1, 2, 3. And so there is a measure in R3. And so what you have here is, say, I is 1, 2. So basically you project everything onto this plane. Right? So to compute the measure of this guy, you take the cylinder set over it, compute the measure in R3, and that's it. Okay, some piece of notations. Nothing very deep. So what then Kolmogorov's theorem or lemma says is that then you can define the measure in a very huge space. I mean, in the space which is, let me denote it just R to 0t, which means all the possible real valued functions over 0t. Over some sigma algebra, which I'm going to denote this way. And it's going to be mu. And this is again probabilistic measure, such that all these guys are just projections of this measure on a huge space. So if the set of parameters was finite or countable, okay, for the finite set there is absolutely nothing in this statement because you just take mu I, where I is the maximal set of indices, right? For the countable set of indices, some work is required. But again, there is nothing deep measure theoretic because if it was countable, then this is just the product, I mean the sigma algebra of the product. So what is deep and somehow not very useful is what happens when the set is uncountable. So what is this tensor product? So this tensor product is by definition the sigma algebra, which is generated by all finite dimensional cylinder sets. So, okay, this is the statement. Actually, this is just a piece of some, whatever, let me say abstract nonsense. Because this is a very small sigma algebra. Let me comment on this. So remark, this is a small sigma algebra. Why? Because any set that needs for its description to involve uncountably many indices is not here. I mean, all the sets describable in these terms are those which involve only countably many variables. Okay, nevertheless, what is good is that if we have a collection of finite dimensional marginals, then we know that at least there is some abstract space with some sigma algebra and some measure such that it has this measurements. Okay, that's the time for the break. Sorry for being slightly late. And then, okay, what is a meaningful statement is this continuity criterion. I mean, okay, we will discuss it after the break. So it was the first reminder here. I mean, just some idea that provided we have distributions for any finite set of indices, there is an abstract space and abstract sigma algebra, so that all the finite dimensional distributions are projection of this huge guy. And it was a remark in the break that actually we do not need, there is nothing specific in R here, so you can take any reasonable space. And there is nothing specific in the time interval here again, so you can consider just abstract set of indices. And moreover, the target space can be different for different indices if you need. So this is fairly general thing. Okay, and then the second reminder is about what I already mentioned during the very first lecture. And this is going to be a special exercise. Again, there is nothing serious here, but just to be sure that everybody is okay with the concepts we use. So what is the exercise? Imagine that we are in the situation, so let we have a family of random variables defined on the same omega. So on the same and imagine that we know, I don't know, from outer space, somebody told us that such that for any event, this is a continuous function. It's a continuous function of 0t. Okay, here? Yeah, sure. So at this point we didn't know anything, it was just an abstract object, but now somebody told us that, okay, as a function of t, this is a continuous function. Then the following are equivalent. So then there are three concepts of measurability one can use. So the first concept is that if I think about this as a mapping from what? From t. Wait. What I would like to say. Nope. Sorry. As a mapping from omega with sigma algebra given to this very abstract nonsense to R to 0t with this abstract tensor product sigma algebra. So I can ask that this mapping is measurable. This is the weakest reasonable thing to ask. So by saying that this is measurable, what I impose is that if I take a cylinder set here, meaning basically only finite set of indices, then, okay, this is measurable event here. So basically I'm asking that all these variables one by one are measurable. The other option is that this considered as a random process is measurable with respect to this product of sigma algebras. So it's measurable like that. So that if I consider omega and t simultaneously, and then write the result. And yet another option is that I can consider this object as a whole, as a function in the space of continuous functions. So this is a metric space. So there is its own Borel sigma algebra, right? So I can ask this mapping with the values in some functional space to be measurable. So the exercise is that all these guys are equivalent. The intuition behind, again, there is nothing very deep here. So the intuition behind is that if we know that the process is a continuous function, then basically the only thing we need to characterize it are the values at, say, rationals, right? So it should be possible to extract any reasonable information just using the values at rationals. Okay, this is a countable family, and for countable families it shouldn't be a big issue. But okay, this is just an exercise to check, we are okay with definitions, etc. Okay, good. And again, the remark here is that in general, of course, B implies A, but not other way around. And the example was discussed during the very first lecture. Why not the other way around? And if we do not know that those are continuous functions, then C is meaningless. So we can just use this language. Okay, so now the theorem. Which is Kolmogorov's continuity with it takes some time to write down, a correct statement. So be patient, please. So what is the setup we deal with? And it's going to be two parts. So let xt be a family of random variables on the same omega, indexed by by some uncountable family, such that for some positive parameters C is of no importance, alpha and beta are of importance, such that for all T, okay, let it be T and S in 0T, we know the a priori information, we know the a priori bound of the difference, of the alpha moment of the difference. So it's bounded by C, T minus S, 1 plus beta. So what is important is that this is greater than 1. I mean, this is the crucial thing. Okay, so let us assume that there is such a bound. Then what I would like to claim essentially is that this is the process with continuous trajectories. That this bound guarantees me that the trajectories are continuous. Unfortunately, as I said, so if we just think about this literally, this is the wrong statement. So I'm going to proceed to the correct statement. Then, for any gamma which should be thought been small, so it should be less than alpha over beta. Other way around, beta over alpha. Almost surely, the following holds. So if I just take the supremum over all t and s, there. But this is an uncountable set. So let me focus on rationals inside of this set. Moreover, let me focus on dyadic rationals of this set, and this is how I'm going to define them temporarily. So those are dyadic rationals. And then, oops. Okay, sorry. Let me write it slightly other way around. So let me write it more in the shape of what we had already. Like this. So I just take t and t plus h, and what I consider is the increment of my process, and put here h minus gamma. What I'm saying is that this is 0. Okay, this is a long line, but what's written? First, I focus only on a countable set of indices. Second, what I say is that at any, essentially, this function is Hölder continuous, right? This is what I claim. So I just consider all the possible increments, and what I'm saying is that they're bounded by h to gamma. Right? Is it clear, the statement? Good. So I think this is the first part. And the second part, now, if I have such a function, if we define xt star just to be the limit over dyadic rationals of this xt. Right? So now if I have a control on some dense set, and I know that the function is actually Hölder, then I can define it everywhere using these points. Then for any given t, they consigned almost surely. So the message is that you do not see any difference between the original family of variables, which is defined, as an abstract stuff, and the very concrete realization is continuous functions. And before proving this is not hard, but I'm going to start with 2 remarks, hoping that they clarify what's going on. I mean, why do we waste time discussing all this? So remarks. So first is on this exponent, on beta. Let xt be a Poisson process. This is another example that we have in our pocket, right? And definitely it is not continuous, right? So this is something about jumps. So if this is a Poisson process, then it is an easy computation. What is the moment of the increments? So basically, this is just the moment of the Poisson variable. random variable. So basically what's here is that this is some constant of alpha by h to the power 1. This is like the expectation of the Poisson variable is h, the second moment is h again, the third moment is h again, etc. So, okay, because of that, it seems that it's important to have beta positive, right? Because that's a counterexample. So this is for any h. So, okay. This is about that. And remark B is, you know, it looks weird. If you never saw it, okay, what happened? I mean, what's the head? Why do we need this x star, etc. So imagine no, I'm going to convince you there is something. I mean, this is not absolutely. I mean, this is trivial, but you know, not tautology. Imagine we already know what the Brownian motion is, and this is our case. So let us define xt in the following way. So this is bt generally. And here is your preferable number of xi is another random variable independent of everything. So independent of bt and say uniform 0, 1. So imagine we already have a nice process and then we modify it slightly in a rather weird way. So we just choose a uniform time and at this uniformly chosen time we do whatever we wish. You can write here 10 or 100 or whatever. Then of course, okay, it is not a continuous function, right? On the one side, we just we just destroyed the continuity. On the other side, it is impossible to see on the level of moments, right, of any expectations. So if you think about any expectations, then they are of course the same. They do not feel this change, right? So this is why this construction is needed to be formally correct, right? Because now what happens is that, okay, we have this xt, I mean, everything is satisfied, here all the bounds are good, but basically you need some modification to recover your continuous function. So, and of course this modification is now bt. Back. Okay. Good. So, as I said, this is not a very hard statement, and basically the second part of Levy's theorem on the modulus of continuity is even more technically involved. And still there are some traces of that proof. What I'm going to do is more or less to repeat the same. So proof. Again, let us just denote it was like this way. First, it might happen that the set of times is unbounded. It doesn't matter, just without loss of generality, let us prove this on the segment 0, 1, then 1, 2, etc. So we can assume that the segment is finite. Without loss of generality, assume it is 1. Then let this be a bad event. And what does it mean to be bad in this context? Let it be the event that x2 minus nl minus x2 minus nk is greater than what? Than epsilon by L minus K 2 minus N gamma. So, okay, that'd be a bad event, and at the end, exactly in the same way, be the union of all over all pairs. And let it be the same way with some delta, though here it is not needed as far as I understand. Okay. And then use this moment. So we had, here we had a bound on the alpha's moment. So just use it to estimate the probability. This happened. So what's this? It is less than some constant L minus K 2 minus N 1 plus beta, right? Over epsilon L minus K 2 minus N alpha gamma, right? So I mean, here is the alpha's moment, and here is the bound. So this trivial. So what I have basically is something that depends on C and epsilon, and that I'm not care about. By, let me put it this way, by 2 minus n 1 minus delta 1 plus beta minus alpha gamma. Whew. I use the fact that L minus K is not that large. Okay? And then the probability that at least one of these events happens is less than the number of pairs K and L minus oops, pardon me. So what is important? The important fact is that this is a strictly positive number. This is the only one restriction we have on exponents, alpha, beta, and gamma, right? So if this is a strictly positive number, then of course I can tune my delta so that everything here is negative, right? Because if it was 0, then what's written 1 minus 1 by something greater than 1, so it was negative. So I have some gap, and I can tune delta. And if I do so, then again I apply Borel-Cantelli. And what I see is that there is some level, which is random, which depends on the sample, such that for any greater n, this does not happen. And then basically I conclude exactly in the same way as it's kept here. Meaning that, okay, for any now t and t plus h, which I need to be only dyadic rationals. Only dyadic rationals now, because I'm focused on the supremum over dyadic rationals. It doesn't help me much with these expansions. Okay, they're now finite. So what I do not need to use is the continuity of trajectories, right? So they're just finite finite expansions. So just write the increment of, I mean, okay, it's not exactly here, but just write t and t plus h in this form, and write the increment from here to there as the increment from here to here plus smaller terms, and sum everything. So it's fairly easy to see that what you have is, is the correct bound. So I'm not going to spend more time on this. So A is done. And here if it's clear, I mean, what should be done? I mean, this is again some portion of estimates, right? But in general, you know, everything converges exponentially here. So if you know that this increment is bounded by k minus L, 2 minus n, everything in gamma, and you know that each of possible increments between, I mean, when you add this term is again 2 minus n minus 1 to gamma, this contributes 2 minus n minus 2 to gamma. Everything converges exponentially. So you just automatically have the same bound, the same Herder estimate. Okay, so A is done now, and to prove B, this is immediate, so you even do not need to have this beta strictly positive. So basically, okay, let me erase something nevertheless. So to prove B, just take some approximations of a given t, of a given general time, be such that, I don't know, they converge very fast. And then note that the probability, okay, the expectation of xt minus xtk to alpha is now less than something exponentially small. In particular, it means that, with some constant in front, in particular, it means that the probability that this is big, I don't know what I should put here, like 2, say, minus k 1 plus beta over alpha. Is it gonna work? Maybe another 2 alpha. Now it seems to work. Less than constant minus k 1 plus beta over 2. So, of course, you know that the probability that xt is actually the limit of xtk is 1. Again, by Barrett-Catelli. So you have some control. So you know that only finite number of these events happen. So in particular, this is the limit. And that's it. So again, an example you can think about, so if it's too hard, so just think about the Poisson process, for instance. What happens? For the Poisson process, we still have, well, I cannot show you. We still have here the bound with, okay, beta equals 0, but it works, right? So what did we prove? We proved that for any given t, with probability 1, there is a limit. I mean, the process is continuous there. Okay? We are on the safe side. This is true. So, okay, here is some picture. So there is this abstract approach. When you can think about your family of random variables defined somewhere abstractly as a random process with continuous trajectories. Okay? And the set of examples why it's needed to consider this modification, etc. Okay, now how does it work with the Brownian motion? Some discussion. Okay, one can construct the Brownian motion using this approach. This is the message. Basically, the most important message, the most important reason why I decided to include this criterion. So, how? Okay, for any given set of indices, T1, T2, Tn, etc., we know how to define the marginal distribution, right? Define to be distributed as the Gaussian vector with the correct, with the covariance matrix we need. Centered Gaussian with covariance mean of ST. Here there is no problem. So in particular, remember it was this oops, it's not there anymore. It was this Kolmogorov's extension theorem. So in particular, you can think about this as a just probability measure in this is a probability measure in Rm. Okay. Moreover, they are of course consistent with each other. So there was this condition that they must be consistent when you project. Moreover, so they are consistent, and this is an easy exercise. Actually, there is nothing to check. So now apply Kolmogorov's extension. So what it gives us, what does it give us? It gives us the space with some sigma algebra and with some measure on it. And this I'm going to think about as my probability space. Right now this is trivial because, okay, I just declared this is my omega, this is my sigma algebra, there is some probability measure, and what are the random variables? The random variables are just coordinates. Okay? But now, of course, there is a question. Okay, I described all the finite dimensional marginals, but if it gives me a random process, something that I can think about as an element of a functional space, and the answer is, of course, yes. So to be sure we're able to think about this as a random process, so what we need to check is this bound on moments. And so we need to check that x t minus xs to alpha is bounded by t minus s power something greater than 1. What do we know about this guy? So we know this is a centered Gaussian with the variance t minus s, right? So take, for instance, alpha bin 4. Then what we know is that basically this is the first moment of the Gaussian variable. And this is exactly 3 to the square of the standard deviation. This is just a computation for the random variable. Okay, this 3, it also follows from the Wick's theorem, if you know what it is. But this is just a computation. Good, so now apply. So we can apply Kolmogorov's continuity with alpha 4 and beta 1. And guarantees us that, okay, now we can think about this as an element of functional space. Think about xt as 1 minus epsilon factor. It's clear? And of course, if you would like to see 1/2, then what you need to do is just increase the power here. So just write that this is some constant m, t minus s, t minus s. Okay. So what we end up with is this space as an abstract probability space, right? With this probability measure, but then with a random variable, which is xt considered as a whole, as a function of t. And we know that this is Herder continuous. Are there any questions so far? Okay, good. Let me just mention it again. Sorry for repeating. So we see several ways to construct the Brownian motion. Somehow this is for purpose. So because what I'm trying to do is not only to prove things about this object, but just to give you a more general intuition that can be useful in other situations. Okay, and now the last thing that is needed to be discussed, I mean, in this circle of ideas, is Donskoy's theorem. So, what is this about? Basically, it justifies the intuition we started with at the very beginning. So, when I told you that the Brownian motion is the scaling can be thought about as the scaling limit of the very simple system in discrete, which is just a simple random walk. So, and then I somehow constructed BT abstractly. I mean, just not saying a single word about the random walk. And again, for real problems, I mean, that we are trying to attack, I mean, not during the teaching, but in our real life. So again, you can think about questions of different sorts. So you can try to prove that some discrete system does converge to something. Okay, this is a question of one sort, which is given by Donskir's theorem. But also you can think quite differently. So you can guess what the limit should be, right? From some intuition, whatever, exactly what I did with random processes. And then just describe the properties of the limiting object, even not knowing this is even not having the proof that this is in fact the limit. So you just have some nice object in continuum and you play with that. I mean, this is another viewpoint. And you know, many people are involved, and some of ours are doing one part, some another, some something third. So that's life. Okay, what's Donskir's theorem? It's also called invariance principle by reasons I don't quite understand. Okay, invariance means that it does not depend on the distribution of a single step. Okay, anyway, this is here the proper name. So let x1, x2, or maybe let me better denote them xi, xi2, etc. be ID random variables with zero mean and finite second moment, which I assume to be 1. Okay, so just all the conditions. I mean, it can have heavy tails, so you don't need to know more. So let now Sn be, of course, just the sum of first n variables. St be the linear interpolation of these Sn's, so be St plus t minus the integer part of t plus 1 minus St. Hopefully this is correct, but again the picture is much more clear. You just take the linear interpolation of your trajectory, and now let us rescale it. So what is the proper rescaling? So let us define the rescaled process as, maybe it's better, not confusing, let it be m, but it doesn't matter. So Stn, let it be just the rescaled version, which is 1 square root over n S Tn. I hope I'm correct. So now the single step now is 1 over n, and the rescaling in this direction is 1 square root of n. And then these functions considered, say, on the segment 0, 1, converge in distribution to the Brownian version. So this is the theorem. Just two concluding remarks for today. The first is that, okay, so marks. The first is that you can view this as yet another way to construct BT. Just take your favorite variable, consider your favorite random walk, and prove this theorem. Okay. If you are able to prove that there is a limit, then you're done. So this is yet another way to construct BT. Second remark is that if you think about xi being standard Gaussian, and n, or okay, here, and n be powers of 2, then basically you have just dyadic rationals, right, and Gaussian distributions there. Actually, this is the same as Levy-Zaselsky construction. Okay, so now what you have here is exactly Gaussian variables. And remark C is about the convergence. What do we mean when we say that these guys do converge to this in distribution? Right, so now all the objects, topology. We have all the objects are continuous functions, right? So we just think about the metric space of all the continuous functions. We think about all functionals, continuous bounded functionals. And what we claim is that if you compute this functional on this trajectory, then it converges to this function computed on the Brownian motion. And what are the functionals in C01? Well, there is Riesz or Riesz-Markov-Kakutani representation theorem, which says that basically those are measures on 0,1. So one of the possibilities is just the mean value. The other possibility is the value at a given point. And there is all the set of measures in between. Okay, so there. That's it for today. Are there any questions? Nope, good.